Actually, Dr. Dhawan has already spoken a lot about engineering geological investigations, assessment, and everything. He has beautifully covered all the aspects like investigations, geological model, and rock mass characterization. And Dr. Rana added that geophysical part, and which is a very powerful investigation approach. And I agree with him that geophysics should come before we take up drilling programs, because it helps optimize the drilling programs and gives more information about the subsurface. And I am always fascinated about that helibone survey, that TEM, where we are able to pick up information from the areas which are inaccessible and difficult to, where the data is not available on ground. So what here I'm doing is, I'm just going because everything has already been covered. So I will just go beyond the usual. Basically, what is being done by different consulting agencies in the country, in the normal geological mapping is being done. And but there are a few things which all these stakeholders need to understand. So let me see. How do I proceed?
Slide move.
The slide move, I'm not getting that. It never happens.
Sir, even an enter will do, sir.
Enter will do.
Enter will do.
I'm doing that. Oh, now it is coming. I did the entering. But anyway, so so now we come to this. Basically, I start this, that what is behind the success or failure of an engineering project? Is it geology, planning, contract, or decision making? So it is mostly in combination of all these four factors, but geology remains at the center of all these things. Now, what are the issues which make a major difference in this failure and success of these things? So basically, these are the subsurface water, the crust mass, the slope sidewall failures, ground stresses, and the deadliest of all, which I consider, is the subsurface water in combination with crust rock mass, and that is the flowing ground. Now, the basic thing for any stakeholder is to know the ground. That is KYG. Dr. Dhawan has already explained that like KYC in vendor-customer relationship, KYG is crucial to engineering team and stakeholders. And this KYG involves basically two steps. One is the diligent engineering geological mapping, and second is the rock mass dissection studies via systematic discontinuity survey with special attention to weak rock zones. I will be concentrating more later on this. And believe me, this is the cheapest and most powerful tool amongst all investigation and exploration techniques. You cover 100% of the project area. You know every square inch of the project, and you are easily able to see what lies below the ground by a very good engineering geological mapping and its different products, which we will be seeing. So what I do, in the engineering geological assessment of a project, I consider there are 5, or afterwards the number of these steps here. We start with internal geology, synoptic geology, engineering geological mapping, reporting, and evolving geological models as infrastructure development takes place at the project and a lot of new data starts coming in. So the stakeholders, the developer, the design engineer, the contractor need an engineering geology team with cutting edge experience and expertise. So the regional geology, I need not go into that. I will just concentrate on this, just focus on one particular value-adding thing, that is the Google Earth images. This is a big tool these days. We will come to this later on. Okay, the problem is this. When I take the cursor, this is not moving. Anyway, so now this synoptic geology is a very important thing because it lays the foundation for the team geology, which will be working there. and sometimes even it can save an infeasible project from taking off. This is the example of a particular project where the tunnel is about 24 kilometers long. And in a short visit of, say, in a couple of days or say about 3-4 days, an expert can just simply find out what are the major issues. Like at this project, there is a thrust here, main thrust. There is a good rock type on this side, which is all gneisses. There is an intermediate sequence of phyllite and quartzites on the downstream side. There is an anticlinal axis here. All these features, and the most important thing is a buried valley here, and you've got the lacustrine deposit where the headworks is to come. Basically, all these things are found out. The synoptic geological map is prepared. It is shared with the team, and where the work takes off. So this is one thing which is very important to be done. Likewise, in the synoptic stage itself, you can prepare a geological section to show what is there in the subsurface. The map was shown earlier. So you can see, like at this particular project, there is a big fault here. There is a buried valley here. You can see there are again gneisses on this side, intermediate sequence of phyllites and quartzites on the upstream side. And things like this is the basic model which comes up within the first site visit by an expert and the young team, which is going to carry out the further work. Likewise, the field photographs which are collected in this stage itself can show you what are the major features here. In this particular photograph, you can see the lacustrine deposit here. The river is going, it's a very wide river, and suddenly you can find that after this place, it is going as a rugged, very narrow stream dropping over some bouldery material, which is basically because of the natural damming here. Likewise, the engineering geological mapping is the most important task that defines the subsurface ground condition, helps layout optimization, design and construction, and reliable products is strongly dependent on the knowledge and experience of the mapping team. So you must make sure that you are getting a team which knows the job and which is able to give it. This is a sample geological map, engineering geological map, which lists out all the possible engineering geological features that are to be picked up in the field. It is a good reference document for the mapping team and for the reviewers as well. Now I go for some tools, which are mapping tools, like stratum contour. So this helps in the projection of a planar feature on ground. And the verification of the trace of the feature of ground vis-a-vis its orientation is another requirement. And the solution lies in joining intersection points of the strike lines of the feature with the contours of same elevations. And the technique comes in handy when the outcrops are scanty. Like in this particular map, there was a project in Arunachal Pradesh. You know the problems. The team was not allowed to leave the road and go to the tunnel alignment area or the project area as such. So they had to contend with geological mapping along the long road here. They picked up all the features here, and all these major lithological contexts, like the one here, between marble and quartzite and schist, all these contexts were projected using the stratum contour method, that how they will go and where we will find these rock types on the other bank of the river. So the stratum contour is a very handy tool which is helpful in working where accessibility is not there. Second important thing is the geological wall logs. Mapping is done. Geological wall logs are usually not very much in use, but they are the most useful tools in geological mapping, and they are most suited for mapping of road cut exposures during progressive mapping. This is a sample of a geological wall log. There are 3 geological logs seen here. So geological logs are basically prepared. You can prepare them all along the road. If there are roads are available, you get very good information from that, or you can use it for projecting the information, spatial information, which you are getting in a particular project area. And you can evaluate these things by photographs and whatever else you can give. The locations are shown in an index mapping. This is again an example of a particular project from where along the road, the mapping has been done. The wall logs have been prepared like this. And from the wall logs, what has been done, the beds have been identified. A litho stack has been prepared. The litho stacks have then been plotted on the tunnel alignment, and with the angle, the tilting has been done with the dip of this. Ultimately, what you get is the tunnel alignment on horizontal slice with all the lithological units. You are getting it. So whatever rocks you could identify, there's a thrust here, there's the gneiss here, there are other rock types, and these are the gray areas where the data was not available on the ground because of overburden cover. Anyway, you can do more work and you can do it. Now I come to the next tool, mapping tool is the satellite images. You can see it beautifully here that a tilted photograph, a tilted satellite image is being used here to show that this area, this is from a PSP, pumped storage scheme, where a upper reservoir has to come on this particular place. And there are some, across the reservoir, there are lineaments. These are the weak zones which have been found to be, say, about 25 to 30 meter wide. And they are the sources of reservoir leakage there. So it is all quartzite on top, which is about 25 meters thick. Down below it is all shade. This is impervious, this is pervious, and mostly secondary permeability because of these lineaments. So these are the things which are value adding in reporting. When you are doing the reporting, it is being done. Likewise, pictures speak louder than words. Everybody knows that. Still photographs in particular, sometimes even videos can do a lot of value adding things, like Dr. Rana just showed that PEM video, which made it more fascinating. So what we do is we give the photograph, and with the photographs on the geological map, the location of the photograph with orientation is given so that the reader can comprehend what is the geological features he is seeing on the map. He can correlate with the data on the geological map, and in the photographs, this is being done. Now, rock mass dissection, I will not go into this. Discontinuity data collection analysis. This is one of the most important jobs with engineering geological mapping. And like you can see in this photograph, you can see that the joints are widely spaced. On the contrary, in this photograph, in quartzite, the joints are very closely spaced. And the most important job is the scan line, which Dr. Dhawan has already described about. And in these scan lines, when you are doing it, so special attention is to be given to the crust fracture zones details, orientation, and thickness. And from this, you will also find out the spacing of these fracture zones and crust zones, which will be of great importance when you are trying to work out the poor and very poor rock masses, rock classes along a tunnel, which will give you that what are the problems and what is the percentage of these particular zones. This is the stereo plot you are preparing after that. And geological sections, again, are the good geological models. In the geological sections, the boreholes, when they are plotted, it is better to give the RQD on one side than the weathering on the other side. And then you can also give permeability in the middle. So these are value-adding geological sections where you can project everything. And these are some specially prepared geological sections like this for a particular project where the tunnel was passing through a deep buried valley. This hole is 580 meters deep, a very real deep hole, and you are getting this lacustrine deposit on below where the tunnel was passing through. It was from a depth of, say, at the bottom you can see 580, and this was covering more than 100 meter thick lacustrine deposit. In the log, it is shown that this is all sand deposit in between. The rounded material, that is the pebble beds, were located at 5 places and 6 places. And this was a place where this carbonaceous material, this was a wood piece was recovered in this, which helped us even do the dating for this material. Likewise, these geological sections during construction are prepared, which, this is for a particular blowout, seepage leakage blowout, from a fractured aquifer in quartzites through an impervious phreatic band, and the tunnel, the TBM, as soon as it passed through this artesian conditions developed here. Likewise, geological sections, the interpreted geological section is given in the beginning when exploratory drift is being done. The geological data is progressively being plotted and shared with the engineers that what they are expected to get in the thrust in the subsurface. The most important tool which I am going to introduce is here is this schematic 3D logs. Because in tunneling, understanding of the weak rock zones assumes critical importance in the success of design and execution, as in association with subsurface water, such zones can turn out to be the nightmares for tunneling crews. So estimation of poor rock classes is made possible through defining the orientation, thickness, and frequency of weak rock zones along the tunnel alignment through systematic discontinuity survey, then constructing schematic 3D logs for estimating weak rock spans and calculating cumulative span of weak rock zones, thus quantifying class 4 and class 5, which is a very difficult thing to do in a tunneling project. This is an example of a project. This is a 3.6 meter span and more than 4 kilometer long HRT in the Himalaya. These are the two the schematic 3D logs of the tunnel, which are given here. And here what has been done, the major sets of weak zones have been plotted here. Because of the orientations of the tunnel, you can see that in this tunnel, in this orientation, the weak zones are spanning a longer span of the tunnel, and because of the orientation with respect to tunnel orientation, it is spanning a lesser length in the tunnel. So the based on the average spacing of 75 meters that was found out from the engineering geological mapping, cumulative span of rock class 4 and 5 worked out to more than a kilometer. That was 29.8% of the tunnel length. So this helps us quantify we are doing that rock mass classification, giving the percentages. So this is schematic 3D logs of the tunnels help you this thing. And the DDAG has come up with an app for doing this work. This will soon be available as a mobile app also, where you can use it and use it in the field. You can use it during the report preparation, during the analysis, and during the construction. It will be very useful. In the construction, I will give you an example here that you can forecast, weak zones from the heading. Like this is a tunnel, you are at this heading at the pole place. You intersect a weak zone here, and using the app, you can find out how this weak zone is going to develop in the tunnel. You can see that this zone we have seen in this particular place. Now, you can tell the tunneling crew that this zone is likely to continue up to, you are there at 25 meters, you can see it is going, say up to about 20 meters more, up to 40, 45 meters, and this is the place where it is coming, so they can plan their excavation, then plan their design. Another example, when you have crossed this zone, you cut another one in this particular corner, you use the app, you can give it that this zone will continue like this, and which can be useful to the tunneling crew. Then reporting is I consider it the most important job in the whole thing, because whatever you have done, if you cannot convey it in a report, then everything is going to be a waste. Maybe it is a write-up, it is the drawings, it is everything. So reporting is an art, and the geology involves personal perception, hence good blend of thoughts and matter is needed. Field observations and interpretations duly supported by facts, data, and documents, including illustrations, are very important. Major construction issues are flagged, and it gives the way forward for investigation and management solutions. And likewise, there are some tools in reporting also. I consider these isometric projections, they are very expressive, scale, and informatic. So this is a tool. Likewise, you are giving these stereo plots in the report. Along with that, if you can give the physical perception of these sets which you have got here, Like in this, that this stereo plot gives us that the channel flow is like this. Now you can see that the joints that you can mostly see, one is dipping in downstream gently or moderately, one is dipping upstream steeply, and the other one is dipping into the right bank. So these things, if you give it, I mean, your report becomes much more expressive to the user. Likewise, you are in the construction of a project, when you are going excavating a slope, you can see that you are identifying these key blocks. I mean, this is a different topic. I have not covered it here. It cannot be. And along with this, if you can see that what kind of wedges and what kind of blocks are being formed, this particular one is very interesting because this is in a diversion channel in a project, at a hydropower project, where these blocks are hard to decipher in the stereo plots. In your kinematic analysis, these blocks can be shown that these blocks create the covering in the bed, because these blocks under the water flow, they float and they come out, they loosen the other blocks and things like that. So this is one evaluation. Likewise, geological models, it is a project. I was talking about a buried valley. You can see that a geological model can show that this is the original river. This is how the natural dam came into being. After natural damming, the water filled up. After the water filling up, sediments starts depositing here. Then afterward, the sediments fill it up. The river now flows at this particular level, falls over this. This is what you could see in the photograph I shared earlier. Then you carry out the drilling. You find out the maximum depth of this particular thing is here. And you carry out, you make a geological model later on that this is the river now. The original flow was, gradient was like this. And now it is flowing at this natural level. Then it is flowing at a general level, very gentle level through the lacustrine deposit. Then steeply over the natural dam. And then again following the usual course. This is like it. And evolving geological models is a continuous process, because as I told you, with the infrastructure, the more and more information keeps coming in, and this is there. And for reiterating the approach for the industry, I would like to say that you start with synoptic geology by an expert. If needed, take hard decisions, even shelving a project if it seems to be that. Although I do believe that technologically we are now able to, to accept any challenge and build anywhere we want. It is to be done. We need a dedicated, focus and alert team geology, dependable input for software analysis, because we are depending more on software these days. But I should not say, but sometimes the inputs are not good, and it is garbage in, garbage out thing. So stakeholders particularly are to keep track of field investigations continuously under expert supervision. So you need to have an expert geologist with you on your team, and better take corrective measures early on. And just to emphasize on the importance of geological mapping, I will just give you a table here. Geology, I say, is the most all-encompassing, cheapest tool. If you consider it, drilling 100 meters quantity, you explore only 5.47 square meter area. It is a point data you get. Basically, pitting, if you do 10 pits of 3 meter into 3 meter, you explore an area of 450 square meters. Drift, if you do 100 meters long drift, 2 meter by 2 meter, it is only 100 square meter area. That is walls, overt, and face you get. In geophysics, give you much better, because 100 meters for geophysics gives you about 1,500 square meter of the subsurface. In mapping, if you do a small area of 100 meter into 100 meter, it is 10,000 square meter you are getting, plus the wall area along the roads and everything. And I will just give you a small figure that 100 meter into 100 meter will cost you something like 5,000 rupees, not much. So thank you very much for your attention. And this is the sincerity you need in geological mapping. This is me taking during those synoptic geology visits at the site and my team took a photograph, which I use it very proudly, that this is the level when I was doing it about just 6 to 7 years back. Thank you very much for your kind attention.